this piece of paper, we know that the length of this side, the longer side, is 11 inches. We also know that the length of the shorter side was 8 inches. Okay? And our question mark on this was, we didn't know how big to make these squares right here. Right? So I'm going to call that X. Because we weren't sure if it should be 1-inch squares or 10-inch, well, it couldn't be 10-inch squares. That's a good question. What is the absolute biggest we could have made the squares? So if we did, could we make it like 5.5? Would we be able to on this side? No. So like a half of 8.5 would be 4.25. You could not make your squares any bigger than 4.25 inches. Because if it were 4.25 inches, that would be like cutting that whole side right there away, and you wouldn't have anything left. So it has to be, your squares have to be smaller than 4.5 inches. Because if they get bigger than 4.5 inches, you know, your square can't come past that like midline right there. Or you can't cut the other square out of the other corner. So if this side right here is X, what I need to do is think about what this looks like when I fold it up. So when I fold it up, it's going to look something like this. Okay? Now, if I think about labeling this box right here, what is going to be the height of this box? Like whenever you think about when you had that flat piece of paper, mine will still unfold right here, right? Whenever you fold that up right there, what was this little piece right here? That was the length of your square you cut out, right? So that means if we don't know what it is, we're going to call it X right there, right? So when we fold this up, that little X right there ends up being our height when we fold it up. Okay? Then I'm going to draw this in right here. This is like the bottom part of your box, right? So we can sort of think, let's go with me. Is there a highlighter on this? Yeah. Like this right here, that bottom part of the box, it's the same as this right here. If you think about taking it from the flat version and folding it up, that part becomes the bottom of the box. So we can label this side right here. And we can also label this side right here. All right, the length of this long side right here was 11. What did I cut away from it? So that whole length of that side was 11. Right, so like from here over to here is 11, just like the length of this side. But if I want to talk about just this piece right here, I started with 11. What did I take away from it? How long? I cut off this piece and this piece, right? Okay. I don't know like a length for that, but what did I call the length of this? X, and I also have an X over here as well. So the length of this side right here is 11 minus 2x. So that's the length of this side of the box. All right, we're going to do something similar over here for the shorter side, for our width. Okay, what is the length going all the way across here? X is just this short piece right here. It's 8.5, right? But this piece right here was X. This piece right here was X. We cut that off. We're only wanting this little piece right here. What could we call that? It was 8.5. And we took away two X's, one on the top and one on the bottom, right there. So this side right here is 8.5 minus 2X. I'm going to put some parentheses around this right here. Okay, does this make sense where I'm getting these from? It's your side length, and then you're subtracting the part that you cut away, which we called X. Okay, so that X is my question mark. I'm wanting to find X. So I need to write a volume formula for this because I want to know what has maximum volume. So how do I find volume of a rectangular prism? Length times width times height. Right? It's one of our more simple formulas that we use. So length is 11 minus 2x. Make sure you put some parentheses around it. Then I'm going to multiply that by width, which is 8.5 minus 2x. Then I'm going to multiply that by height, which is x. Okay. From here, we are going to use Desmos for this. Okay. So if you don't have your computer up, I'll just pull it up here. So we are going to type in that formula. And we probably don't want to use a V. I think it's not going to graph it right if we use a V. Just call it y equals 11 minus 2x and 8.5 minus 2x and x. Now, you've got a crazy graph here. But do we want to like look over here where we're like way over here? Can we cut a corner out that is 6.734 inches? What do we say our biggest corner we could cut out was? 4.25, and really we couldn't even get quite to that, right? So so if I look at my graph, 4 is like right here. So and would it make sense to say we could cut out a negative? Can't cut out negatives, right? So really from 0, like not cutting out anything, just a flat sheet of paper, to up to 4.25 is all we can really look at. So I'm going to change my view here. So I'm only looking at that part, and then I'm going to make my y a little bit bigger. So we're looking at this part of the graph right here. All right, so if I want to figure out the exact value that I should use, I can click on this right here. It is going to give me a point that is the maximum point right there, and 1.585 is what we should use for our x. So, oh wait, that's the wrong thing. That's one up. Go back to the right thing. That's also the wrong thing. Here we go. So the maximum would be 1.585 inches. Okay. The maximum volume, it didn't ask for this. Actually, no, it says, all right, so that, instead of saying that that's maximum, I should say the maximum happens whenever you cut out 1.585 inches. The question said, what is the maximum volume of the box? So if we go back over to Desmos really quickly, that maximum, the x-coordinate was 1.585. The y-coordinate is your volume, 66.148. So max volume is 66.148, and that would be cubic inches. Who had 66? Yours. What was your height of your 1.68? So you were very close to having this right here. If you got a volume bigger than 66.148, you measured something incorrectly, because you should not be able to get a volume any bigger than that. That's the absolute largest box that you can get right there. Now, if you were doing arts and crafts and trying to make a paper box for whatever reason you would need a paper box for, then you would not necessarily need to do this, right? But let's say that you were in charge of manufacturing packaging for something like cereal, and you are going to make cereal boxes for millions of boxes of cereal, right? And this is the best, like the most efficient use of your packaging, because you get the biggest volume for the smallest amount of material made, which a lot of times is actually not how they do things, because they want the package to look bigger, and they don't care if they waste a bunch of materials, because you will think more is in it and you'll buy it. But I will say that, if Andrea holds hers up here, that's kind of cereal box looking, right? I mean, it'd be too small to be a box of cereal, but as far as proportions go, it looks a little like a cereal box, right? So if you're making millions and millions of these, and you're working in a manufacturing plant that is you're designing for a manufacturing plant to make something like this, you have to make those calculations and make those like cost analysis. You would have to go further with this. You would need to know how much each sheet of cardboard cost, and what if we decide to use a bigger sheet of cardboard to use different dimensions, how much more would it cost us for packaging? There would be a lot of calculations that could go into this to make sure that you are doing what you think is best for the company as far as this goes. Now, again, arts and crafts, not really necessary for you to know that. But if you're talking about scaling this up where you're doing a lot with it, then it would matter a lot for that. Okay, so let's do a couple more problems of this. We're not going to make any more boxes, but we're going to do a couple more problems where we practice doing sort of the same thing. Okay, so if we go to the next one here. All right, so a grocer, the person who runs the grocery store, wants to sell fruit in boxes that are cut from a 36-inch square of cardboard. If he makes a box that has a height of 4 inches, what will the volume of the box be? So this is not a problem with an X. This is a problem where you have to figure out the actual volume. This box already exists. They do not give you a lot of measurements here. What we have to do is we have to decide what the measurements on this flat piece are going to be once you fold it up over here for the box, right? We need length, width, and height of that box. The easiest one to find is the height. So this side right here, whenever you fold it up, what is that going to be? It is going to be 4. It's going to be this height right here of that corner cut out. This is a little bit different because this box has a lid, so it's a little bit different. But this piece right here is 4. And when you fold it up, this folds in right here, that folds in. And all these little pieces right here, this would also be 4. This would be 4. Let's mark everything that would be 4. That's 4. This piece is 4. 4. These are 4. I think that's everything we need. And all of that's going to get folded up. So 4 inches is our height of that box. All right, let's talk about this piece right here, this long side of the box. Where is that on this diagram? 36 is the length all the way across. You're close. You got to subtract 4 twice because, like, right here, the piece we're talking about, this piece right here, let me use a different color, actually. This piece right here is going to be like this length right here, which this whole side right here was 36 because this was a square piece of cardboard. You cut 4 off on both ends. So if we do 36 minus 4 minus 4, then we'll get, what, 28? So this piece right here is 28 inches. So that is the length of this side. Okay. Then the last piece that we need is the width right here. All right. This is the hardest piece to find. On this, what piece are we talking about here? Where if we were going to point that out? Yes, like right here beside the L? Yes, we're talking about like this length right here. Or this length right here, right? Those two pieces should be the same because the top of the box and the bottom of the box are the same. Okay? Yes?
But you minus the 36 by 8, and then you divide the answer by 2. You get your answer.
Perfect. Because what you've got here, this piece right here was 4. This piece right here was 4, right? And so we got 36, and we got to take away 4. That leaves us with 28. But that's split between this bottom and the top, right? So we divide that by 2, and we will get 14 inches for that piece right there. Now, that is kind of difficult to do, to think about. But now that we have those values, volume should be very simple for us, right? Because this is just volume of a box. So, Shay, what is our volume formula for a rectangular prism or box? Very good. And so, length would be 28, width is 14, height is 4. We are going to type that into our calculators for this. 28 times 14 times 4 is going to be 1568. So we got volume equals 1568, and that would be inches cubed. Oh, I did this on the wrong. Oh no, I didn't. I just flipped pages. Is what happened right here when I didn't mean to. We're on. Oh, does that? You have example 3 twice. Okay, this is the first example 3. That should be a 2. I need to go back and fix that. This is the one that has the 4 on it. The next one's going to look exactly the same, but it's going to be a different question. All right, questions so far? Now, that was with a given value. Let's look at a similar problem, almost exactly the same type of problem. What's the only thing that I changed? I no longer know that this is 4 inches. I now know that it is X inches. All right? So, everywhere we used a 4 in the last problem, we now don't assume that it's 4. We have to say that it is X. So that means this little piece, this little piece right here is no longer X, no longer 4, it is X, which was my height of this box. It is now X, right? So all of these little pieces like that are X right here, right here, right here. All those little pieces that have that same length have to be X. So the front, like that length of the box here, that was this side right here. So to get that on the other problem, we did 36 minus 4 minus 4. What have we got to call it for this one? And we'll not get a number. It's 36 minus what? 2x. You got to do 2 x's because you're cutting the x off of either end, right? You're subtracting out this x and this x. So this side right here is 36 minus 2x. All right, now the hardest one to find for sure is this one. I need to know what that length or the width of this box right here would be. So, what do you guys think? Okay, how did you get 18 minus, well, I don't think you're quite right. Why'd you use 18 instead of 36? Okay, so if you divide it by 2, if you cut 36 in half, right, that would be like, oh, we're cutting the box in half right here. This right here is 18. Do I need to subtract 2x from that? No. I would just subtract a single x from that, right? So 18 minus x. Another way we could do this is we do it kind of like Elijah did. He did 36 minus 8, which is like our 2x, right? And then he took that and divided it by 2. If you do that, if you divide 36 by 2, you get 18. If you divide 2 by 2, you get 1. And you get 18 minus x that way also. Or you can leave it like that as a fraction. Just keep it in parentheses if you do it. Okay, are we okay here? All right, so if you can get to this point, the last part's not that bad, okay? Because volume for a box is very simple. What do we do for volume? Length times width times height. So that means we're going to do length, which is 36 minus 2x. Just make sure you keep everything in parentheses. Width, which is 18 minus x. And height, which is x. Okay? At this point, we're letting Desmos do the work for us. So I'm going to go over to Desmos. I'm going to type in this equation, do a y equals instead of v equals, or it won't do it correctly. We're going to do 36 minus 2x times 18 minus x times x. And let's see. Zoom out some here. The volume of this is much larger. Now, I do go all the way out here to like 18. Can I cut 18-inch corners out of that square that's only 36? No, the whole thing would be gone. All right. So you don't want to like look past this point over here. We want to look at this maximum that falls right here. To find a maximum on Desmos, it is so easy. The hardest part is getting zoomed correctly. But once you're zoomed in correctly, you just find the highest point. It's going to put a gray dot there. You've got 6, which is the width of the squares you should cut out. And 1728 is your maximum volume. So let's see what it asks us for there. What should the height of the box be if you're wanting maximum volume? So it should be 6 inches. It didn't ask for the maximum volume on that one. It just asked what that height should be. So you would just give 6 inches as your answer. If it asked for the volume, we'd put 1728. I think this stuff is so cool that you can find that exact amount that you would need for something like this. Now, certainly, it's not necessarily an everyday skill, but I love to learn about things that are used out there in the real world, even if I'm not the one necessarily using them. And you guys still have your whole lives ahead of you. Who knows where this world may take you? Some turn of events may have you working somewhere where you're doing something of this nature. I am pretty certain at this point in my life that's not going to happen to me. I guess anything could happen, but probably not for me because I've made a lot of career choices that I plan on riding out to the end. But you guys have a lot of things that you might decide to do that could possibly land you doing something like this one day. Now, probably not most of you, but, one or two, you never know, could possibly end up doing something like that. If you ever do, I'm going to tell you this right now. I love math so much. It is my favorite. I like teaching math. I love the idea of, these types of things being used in the real world. Sometimes I am jealous of people who have other jobs that do cool math in their jobs. Because I wish, a little piece of me wishes, I wish I'd done that, and I wish I'd done that, and I wish I'd done that. I'm pretty happy with my career choice. I really like teaching. You know how, that some dads, played football in high school and they were, number one, and they were the best, and then what are they going to do whenever they have a little boy? They're going to be, signing them up when they're 5 years old and training them to be the very best because they are reliving their childhood through their child. I want to do that with you guys as well. I want to live vicariously through you. If you grow up and you have a job where you're doing something like this, I need you, if I'm still here at Elkin High School, to find me and come tell me about the math that you're doing because I would love to see it and maybe use it in my class if I can, or if it's something too hard for the class to do, I still want to see it because I think it's cool to see the tree. Huh? I would let you come back in and teach the class if you have something cool that we're doing. Well, then you're probably not going to have that job for long. Yeah, that is math. It's probably percentage sort of stuff is going to be where that comes in, and that's probably more 7th and 8th grade math that they use that for. But I want to know anything you run into. Send me an email about this one day. Remember this moment. If you find yourself in your adult life doing math, and you're I never thought I'd use this again, but here I am using it. Somebody find me and send me an email because I want to know about it. I never get many of these emails, but I would love them so much. Plus, I am a teacher. Obviously, I do not work at a manufacturing plant for packaging. So, I don't know exactly what they're doing there or if they're figuring this stuff out. Theoretically, definitely it could be used, but I love real-world examples where people are actually doing them for that. All right. Let's see. We got just a few more minutes. Let's try this one. You can keep them as a treasure or put them in the recycling on the way out, whichever you prefer. But we're going to wait. We're going to do this one more example right here, okay? One more example. You can keep them as a treasure forever. Use them to gift wrap presents for your friends and family. I don't know. Or you can put them in the recycle whenever you leave. All right, so let's do this one more problem, and then we're going to move on. Be time to go. So a company is manufacturing an open-top rectangular box. They have 30 centimeter by 16 centimeter sheets of material. The bends are made by cutting squares the same size from each corner of a sheet, bending up the sides and sealing the corners. Create an equation relating the volume of the box to the length of the corner of the X cut out. Graph this, identify the maximum, identify the domain, okay? So, let's actually start with domain first. So, if I call this right here X, actually, they've already done that right there. All these little corners right here are X. What's the very biggest X could be? 8, right? Because you have to take your shortest side, and it can't be more than half of that shortest side, right? Because if you tried to cut a 9-inch centimeter corner out of here, you wouldn't be able to cut the other side out, right? So, what's the very smallest it could be? It could be smaller than that. It could go 1/2. 0 theoretically, right? Like, if it's 0, you're really not doing anything. So you would say from 0 up to 8, you would use parentheses for both of these because you can't actually have 0 and you can't actually have 8. Because if you cut 8 out, there'd be nothing left. All right? So, whenever we look at our graph, we really only want to look between 0 and 8 because anything else doesn't make sense for this situation. So, I know that that little corner, because we've done this a couple times, is my height of this box. The length on this side, let me use a different color right here, that would be this longest side right here or down here. What is that going to be? It is 30, because that's the length of this whole side, minus 2x, because you cut an x off of each side. Okay? The width of this box, we'll use blue for that, that is this side right here of your figure, or this side over here, either one. What could I call this side? 16 minus 2x. Okay, so to write a volume formula for this, right, boxes are just length times width times height. We just have to multiply those three things together. So 30 minus 2x, 16 minus 2x, and x. Everybody okay there? All right, the last thing we want to do is to put this into Desmos. So if we do 30 minus 2x, 16 minus 2x times x, it is going to give us this graph. I need to see the maximum of this. Right there it is. And what did the question ask us for? It says, graph the equation, identify the dimensions of the box. Dimensions that will have maximum volume. So is it asking for the x or the y? The dimensions that will give maximum volume. The dimensions are the lengths of the sides. So it's asking for that 5.33. It actually wants all the dimensions. So that would be, oh sorry, your x would equal 5.33. You could do the length and the width too. The length, you'd have to do 30 minus 2 times 5.333, which would be 19.333, and then the width would be 16 minus 2 times 5.333, which would give you 5.333. So those would be, I guess I should call that height right there. So those would be your dimensions. I should be putting centimeters on this. Okay. So your boxes you may either take with you or throw in the recycling. Put up your calculator. Just leave your ruler and your scissors on your desk. There is no homework tonight. Looking over that Delta Math is a good idea. This will not, the box stuff with the corners is not going to be on the quiz tomorrow. It'll just be volume and cross section. We're not ready to do that yet.